Okay, thank you very much. So thank you very much, Kasia, for the nice introduction, and good evening, everyone. My name is Giorgio Mattana, and I work as an associate professor at Université Paris-Cité. But today, I'm mostly here as a member of the PrintUp Institute. So before going to the scientific content of my presentation, I would like to introduce you briefly the PrintUp Institute. So PrintUp Institute is a research project that started a few years ago, and it is led by a group of scientists, including me, affiliated to Université Paris-Cité. And the main goal of this project is the development of the value chain around the theme printed electronics for health applications. So to do so, our project actually relies on the scientific expertise of a group of scientists, including me, also supported by a huge technological platform devoted to printed electronics. And we also have a huge networks, including scientists, but also medical doctors and device manufacturers. So if you have any questions about this topic, printed electronics for health application, please feel free to get in touch with me. So now back to science, I'd like to start my presentation by introducing the context of my research activities. And this context is represented by the current energy crisis. So we all know that today's world is facing a huge energy crisis caused by the depletion of traditional fossil fuels sources, but also by the environmental degradation caused by climate change. And this crisis is pushing researchers towards the quest for efficient and environmentally friendly and renewable energy sources. And it is within this context that thermoelectric materials and generators find their place. So a thermoelectric generator can be simply defined as a thin layer of a thermoelectric material sandwiched between two electrodes. And its most important property is that when we apply a temperature difference at the extremities of this thermoelectric material, then the device reacts by producing a voltage, which is called thermal voltage. So thermoelectric generators can be seen as energy harvesters, capable of recuperating a part of the thermal energy of their environment and converting it in usable electric energy. At the moment, the best performing thermoelectric materials are listed here. They all belong to the family of inorganic semiconductors, and they all have very good energy conversion efficiency, but they also have some important drawbacks. First of all, most of them are highly toxic. They also exhibit poor mechanical properties because they are brittle. Most of them are based on rare materials, and they all require complex fabrication techniques, meaning that devices based on these materials are typically very expensive. So at the moment, there is a strong need for less toxic, low-cost thermoelectric materials exhibiting better mechanical properties. To reply to this need, at the PrintUp Institute, we decided to start the fabrication of thermoelectric generators by using organic semiconductors. Organic semiconductors are indeed much less toxic. They exhibit better mechanical properties because they are flexible. They can be deposited, most of them, in ambient conditions, and most of them can be also processed in liquid phase. And these last two advantages strongly suggest the possibility of using printing fabrication techniques for this type of devices, such as inkjet printing and screen printing. So if you take a look at the current state of the art, you see indeed quite a lot of papers reported on printed organic thermoelectric generators. The large majority of these devices are hybrid devices in which printing techniques were used just for the fabrication of a part of the generator, usually the electrodes, in some other cases, the organic semiconducting layer. And many different substrates were used. In the majority of cases, rigid substrates such as glass slides or silicon wafers. You have to wait until very recently, so